Picture this: a pitch-black sky suddenly ripped open by an explosion of light so brilliant it outshines every star in the galaxy for a fleeting moment. This isn't science fiction. It's a gamma-ray burst, one of the universe's most violent and elusive spectacles, visible only once in a million years. And it's just one of the jaw-dropping cosmic miracles waiting to unfold above us if we know where and when to look. The universe is a stage, and every so often it puts on a show so rare, so breathtaking, that missing it would feel like turning away from history itself. Think about the last time you stood under a clear night sky, staring up at the quiet dance of stars. Now imagine witnessing something so extraordinary it rewires your understanding of time and space. Maybe it's a comet streaking past, its tail glowing like a celestial brushstroke, or a planetary alignment so precise it feels like the cosmos lined up just for you. These aren't just pretty sights, they're cosmic rarities, some occurring once in a lifetime, others once in several lifetimes. And the best part, you don't need a telescope to catch many of them, just the right moment, the right place, and a sense of wonder sharp enough to recognize magic when it happens. That's exactly what this journey is about. Over the next 25 revelations, we'll traverse the most astonishing, unpredictable, and downright mind-bending events the universe has to offer. From eclipses that paint the sun black to meteor showers so intense they look like the sky is falling, each of these phenomena carries a story, a fleeting invitation to witness the universe at its most dramatic. Some defy physics as we know it, others whisper secrets about our place in the cosmos, but one thing ties them all together. If you blink, you might miss them forever. So let's dive into the spectacle. The clock is ticking and the cosmos won't wait. The night of December 21st, 2020 was no ordinary winter solstice. As twilight settled, something extraordinary unfolded in the southwestern sky, a shimmering, almost surreal glow where Jupiter and Saturn, the solar system's two largest planets, appeared to merge into a single radiant point of light. This was the Great Conjunction, a celestial hug so tight it hadn't been witnessed this closely since the year 1226, when night still roamed Europe and astronomers peered at the heavens with nothing but their naked eyes. Conjunctions happen when two planets share the same right ascension, a fancy way of saying they line up from our earthly viewpoint, but this wasn't just any alignment. Jupiter and Saturn, often called the kings of the solar system, typically pass each other like distant ships in the night, separated by at least a finger's width in the sky. This time, they defied expectations, closing the gap to a mere 1/10 of a degree less than the thickness of a dime held at arm's length. The result was a dazzling, double-planet effect, so striking it sparked whispers of the legendary Star of Bethlehem, earning it the nickname the Christmas Star. What made this event truly once in a lifetime wasn't just the rarity, it was the sheer accessibility. You didn't need high-powered telescopes or a PhD in astrophysics to be awestruck. Families gathered in backyards, urban stargazers squinted past city lights, and even smartphone cameras captured the duo gleaming like a celestial diamond. For weeks leading up to the climax, the planets staged a slow-motion dance, inching closer each evening, a cosmic countdown visible to anyone who glanced upward. But why 800 years between such close encounters? It's all about orbital rhythms. Jupiter laps the Sun every 12 years, while sluggish Saturn takes nearly 30. Their paths intersect only every 20 years, but precise alignments demand near-perfect geometry, a celestial game of chance where timing, angle, and perspective all collide. The next comparable event won't grace our skies until the year 2880. So for those who witnessed it, that fleeting glow wasn't just a pretty sight, it was a handshake across centuries, a reminder that the universe keeps time on a scale far beyond our own. On August 21, 2017, Day turned to night in the middle of the afternoon as the moon's shadow raced across the United States at nearly 1,700 miles per hour. From the Oregon coast to the beaches of South Carolina, a 70-mile-wide ribbon of darkness, the path of totality swept diagonally across the continent, turning ordinary towns into stages for one of nature's grandest performances. For those standing in that narrow corridor, the world transformed. Temperatures dropped as much as 10 degrees in minutes. Birds fell silent, thinking sunset had arrived early. Streetlights flickered on, and the sun's wispy corona erupted into view, a halo of plasma stretching millions of miles into space. What makes a total solar eclipse so spellbinding isn't just the celestial mechanics, though those are impressive enough. It's the perfect cosmic coincidence that the sun, 400 times larger than the moon, also happens to be 400 times farther away. This precise ratio means that when they align, the moon can completely obscure the sun's disk while allowing its ethereal outer atmosphere to shine through. Unlike partial eclipses where the sun appears as a crescent totality, reveals phenomena invisible any other time, solar prominences, fiery loops of plasma larger than Earth, leap from the sun's edge. The sky turns an eerie twilight blue at the horizon, while directly overhead, stars and planets emerge in midday. The 2017 event became America's most witnessed eclipse in history, partly because its path crossed 12 states and major cities like Nashville and Kansas City. Roadways jammed as millions embarked on eclipse pilgrimages, chasing clear skies. In Casper, Wyoming, traffic backups stretched for 20 miles as visitors flooded a town with a normal population of 60,000. One couple drove non-stop from Florida to Idaho, sleeping in their car to ensure they wouldn't miss the 2 minutes of totality. The collective gasp from crowds when the sun vanished became a viral sensation, a shared moment of awe transcending age, language, and background. Beyond the spectacle, the eclipse sparked scientific discoveries. Citizen scientists armed with smartphones helped map temperature changes across the path, while researchers documented bizarre animal behavior, spiders dismantling webs, cows returning to barns, and bats emerging confused. The event also revived historical fascination. Newspapers reprinted accounts from 1918, the last time a coast-to-coast eclipse occurred. Now another chance looms. On April 8, 2024, a new path of totality will carve from Texas to Maine, lasting up to 4.5 minutes, nearly twice as long as 2017. Cities like Dallas, Indianapolis, and Cleveland lie directly in its path, offering millions more the chance to stand in the moon's shadow without traveling far. But eclipses are fickle. Cloud cover, timing, and location make each experience unique. Those who saw 2017's eclipse often describe it as life-altering, a humbling reminder of our place in a clockwork universe. For those who missed it, 2024 isn't just another astronomical event. It's an invitation to join one of Earth's most exclusive clubs, those who have stood in darkness beneath the sun's stolen light. On June 5, 2012, skywatchers around the globe fixed their eyes and telescopes on a tiny black dot creeping across the face of the sun. This wasn't a sunspot or a stray asteroid. It was Venus, Earth's closest planetary neighbor, performing one of the rarest ballets in our solar system, a transit. For nearly 7 hours, the planet traced a slow, precise path between Earth and the sun, appearing as a perfect in-chi circle against the solar disk. But this wasn't just a celestial curiosity. It was a fleeting moment of cosmic geometry, one that wouldn't repeat for over a century. What makes Venus transits so extraordinary is their absurd infrequency. While Mercury skims across the sun's face 13 times per century, Venus transits arrive in pairs separated by over a century. The last duo occurred in 2004 and 2012. The next won't grace our skies until December 10, 2117 and December 8, 2125. This bizarre pattern stems from the planet's tilted orbits. Venus circles the Sun every 225 days, but its path is tipped just enough that it usually passes above or below the Sun from our viewpoint. Only when Earth, Venus, and the Sun align with razor-thin precision, a celestial syzygy, does the transit occur. Historically, these events were more than spectacles. They were scientific gold mines. In 1761 and 1769, astronomers mounted global expeditions to time Venus's transit from different continents. By comparing their observations, they cracked one of astronomy's biggest mysteries, the scale of the solar system. Using a method called parallax, they calculated Earth's distance from the Sun with unprecedented accuracy, 93 million miles, a figure still used today. Captain James Cook even sailed to Tahiti in 1769 to record the event, kicking off Europe's exploration of the South Pacific. Modern observers in 2012 witnessed a far different experience. Armed with solar-filtered telescopes and live NASA feeds, millions tracked Venus's entrance as it indented the Sun's edge like a thumb pressing into an orange, an effect called the black drop. For 6 hours and 40 minutes, the planet's silhouette marched across the Sun, its atmosphere briefly glowing as sunlight bent around it. Unlike Mercury's tiny, fast-moving dot, Venus appeared 3 times larger, its passage slow enough to watch in real time. Yet the true magic lay in the event's rarity. Those who saw it knew they were part of an exclusive club, one that won't admit new members for another 93 years. As Venus exited the solar disk at sunset in some parts of the world, it marked more than the end of a transit. It was the closing of a cosmic curtain, leaving behind a century of darkness before the next act begins. On January 20, 2019, the night sky delivered a triple cosmic threat, an event so visually stunning it sent photographers and stargazers scrambling for their gear. That evening, Earth's shadow swallowed the Moon whole, transforming it into an eerie crimson orb while simultaneously appearing 14% larger than usual. This wasn't just any lunar eclipse, it was a super blood moon, a rare convergence of celestial mechanics and perfect timing that painted the heavens with a palette unlike anything seen in years. The magic began with the supermoon. When the moon reaches its closest point to Earth, known as perigee, it can loom significantly larger and brighter in our sky. This happens because the moon's orbit isn't a perfect circle. It's an ellipse that brings it as close as 225,000 miles or as far as 252,000 miles from Earth. During January's eclipse, perigee coincided with the full moon, creating a supermoon effect. But the real show started when Earth slid directly between the Sun and Moon, casting our planet's shadow across the lunar surface. Here's where things get dramatic. Unlike a solar eclipse where darkness falls abruptly, a lunar eclipse unfolds like a slow-motion cosmic painting. As the moon entered Earth's umbra, the darkest part of our shadow, sunlight filtering through our atmosphere, got bent like a prism, scattering blue light and allowing only red wavelengths to bleed onto the moon's surface. The result, that iconic blood moon glow, ranging from coppery orange to deep brick red depending on atmospheric conditions. Volcanic eruptions or wildfires anywhere on Earth can intensify the hue by adding extra particles to the air, a fact that gave ancient cultures plenty of reason to interpret these events as omens. Photographing this spectacle required equal parts preparation and creativity. Seasoned astrophotographers used DSLR cameras with telephoto lenses mounted on tracking tripods to compensate for Earth's rotation, while smartphone users tapped into night mode features and makeshift tripods. The key challenge, balancing the moon's bright supermoon phase against its dimmer, shadowed state. Many bracketed exposures taking multiple shots at different settings, then blended them later to capture both the crimson eclipse and the surrounding starfield. Social media erupted with time lapses showing the moon's transformation from silver disk to rust-colored marvel, some even capturing the dimming effect as Earth's shadow crept across craters and lunar plains. Beyond its visual splendor, the 2019 event stood out for its timing. Unlike brief solar eclipses, totality lasted over an hour, visible from the Americas to Western Europe, a leisurely window for observation. Families gathered in backyards with binoculars, while astronomers live-streamed the event to millions. For indigenous communities, it revived traditional stories. Some Navajo cultures viewed eclipses as a time for quiet reflection, while Inca legends saw the crimson moon as a jaguar attacking the lunar surface. And here's the kicker: while lunar eclipses aren't as rare as their solar counterparts, the super blood moon trifecta won't happen again in exactly this configuration until May 26, 2021. But even then, atmospheric conditions, geographic visibility, and the moon's exact distance will paint a wholly unique portrait. That's the thrill of celestial events. No two performances are ever quite the same. Every May, as the Earth plows through a river of cosmic debris left behind by history's most famous comet, the night sky erupts with streaks of fire, the Eta Aquarid meteor shower. These aren't just random space rocks burning up in our atmosphere. They're fragments of Halley's Comet, a celestial time capsule that's been unraveling across the solar system for millennia. When these tiny particles, some no larger than grains of sand, collide with Earth at 148,000 miles per hour, they ignite into brilliant trails, some glowing vivid yellow or green as they vaporize. What makes the Eta Aquarid special isn't just their speed or their pedigree. It's their radiant point, the spot in the sky where the meteors appear to originate. Look toward the constellation Aquarius in the pre-dawn hours, and you'll see them racing outward like sparks from a celestial wheel. Unlike slower showers, these meteors blaze across the sky at breakneck speeds, often leaving glowing ionized gas trails that linger for seconds. Under perfect conditions, observers near the equator can spot up to 60 meteors per hour, while mid-latitude viewers might catch 30. The real magic lies in the shower's connection to Halley's Comet itself. Every 76 years, this icy wanderer swings by Earth, leaving fresh debris in its wake. The Eta Aquarids and their autumn counterpart, the Orionids, are like breadcrumbs marking its path, a reminder that even when the comet isn't visible, its legacy lights up our skies. Halley last appeared in 1986, and its next grand performance comes in 2061. But you don't have to wait nearly 4 decades to feel its presence. Each spring, those dusty remnants deliver a preview, burning up as if to say, the main act is still coming. For the best views, escape city lights and let your eyes adjust for at least 20 minutes. Unlike eclipses or planetary alignments, meteor showers reward patience. Spread a blanket, lie flat, and let your gaze wander, no telescopes needed. The meteors can appear anywhere, though they'll always point back to Aquarius. Early May mornings typically offer peak activity, often around May 5th or 6th. And here's a pro tip. The shower's name comes from Eta Aquarii, a specific star in Aquarius, but you don't need to find it. Just face east before dawn and wait for the sky to dance. There's something humbling about watching comet dust from centuries ago flare into momentary brilliance. It's a cosmic hand-me-down, a reminder that the universe recycles everything, even light. So when you see an Eta Aquarid streak past, remember, you're not just witnessing a space rock's fiery end. You're seeing a piece of Halley's Comet keep its appointment with Earth right on time, as it has for thousands of years. And in 2061, when the comet itself returns, today's meteor watchers might just point to the sky and say, we've met before. The night sky of early 2023 offered a visitor unseen since the last ice age, a glowing green wanderer named Comet C 2022 E3 ZTF. Discovered just 10 months earlier by astronomers at the Zwicky Transient Facility in California, this ancient iceberg of dust and gas swung within 26 million miles of Earth, close enough for backyard stargazers to spot its eerie emerald hue without telescopes. Its color wasn't just for show. That verdant glow came from diatomic carbon, a rare molecule that vaporizes in sunlight, creating a luminous green halo around the comet's nucleus. For scientists, this wasn't merely a pretty light show. The comet acted like a cosmic time capsule, carrying chemicals unchanged since the solar system's infancy. Its 50,000-year orbit meant the last time it approached Earth, woolly mammoths still roamed the plains, and Neanderthals shared the planet with modern humans. When it streaked past the North Star in late January, researchers worldwide trained spectrometers on its tail, analyzing sunlight filtered through its gases to decode the primordial recipe of our early solar system. Tracking this visitor required perfect timing. Unlike predictable meteor showers, long-period comets like E3 ZTF arrive unannounced and depart for millennia. By early February, it had faded from naked eye visibility, but not before etching its legacy in astrophotography. Social media flooded with time lapses of its curved dust tail, stretching like a celestial brushstroke across constellations. Some images even captured a rare anti-tail, an optical illusion where sunlight reflected off dust particles, made it appear the comet had tails pointing in opposite directions. The real marvel, its accessibility. While many comets demand dark skies and expert equipment, this one peaked at magnitude 5, visible from suburban backyards. Stargazers used simple tricks, looking slightly away from the comet to engage the eye's light-sensitive rods, or holding up binoculars to reveal its fuzzy green coma. Its closest approach on February 1st coincided with a new moon, offering perfect darkness though light pollution still challenged urban viewers. What made E3 ZTF unforgettable wasn't just its rarity or hue. It was the profound sense of connection it sparked, a reminder that the same cosmic snowball once witnessed cave painters and now gleamed for smartphone-wielding humanity. Unlike Halley's Comet, which returns like clockwork, this green stranger won't grace our skies again for another 50 millennia. Those who saw it didn't just witness a comet. They locked eyes with a relic from the dawn of human history, now vanishing back into the cosmic dark. In July 1994, humanity witnessed something unprecedented, a cosmic train wreck in real time. Comet Shoemaker-Levy 9, a fractured remnant of what was once a single icy body, didn't just pass near Jupiter. It dove straight into the gas giant's atmosphere in 21 explosive pieces, each impact unleashing more energy than all the world's nuclear arsenals combined. The largest fragment, Fragment G, hit with a force of 6 million megatons of TNT, creating a fireball 3 times Earth's diameter and scarring Jupiter's cloud tops with dark bruises that lingered for months. This wasn't just a light show, it was a masterclass in celestial violence. The comet's fate had been sealed a year earlier when Jupiter's immense gravity ripped it apart during a close pass, turning it into a string of icy pearls orbiting the planet. Astronomers quickly calculated the fragments would crash into Jupiter's southern hemisphere between July 16 and 22, 1994, marking the first time scientists could predict and observe a planetary collision. Telescopes worldwide, including the Hubble Space Telescope, trained their lenses on Jupiter as the fragments arrived like clockwork, some hitting at over 130,000 miles per hour. The aftermath revealed more than scorched clouds. Infrared telescopes detected temperatures soaring to thousands of degrees at impact sites, while spectroscopic analysis showed water, sulfur, and carbon monoxide chemical fingerprints of the comet's composition. But the real revelation was the scale of devastation. Dark impact plumes rose over 1,000 miles above Jupiter's clouds, and the resulting scars stretched wider than Earth itself. For planetary scientists, it was a sobering simulation of what similar impacts could do to our own world. Jupiter, with its massive gravity well, often acts as the solar system's cosmic vacuum cleaner, drawing in dangerous debris. This time, it showed us exactly how that protection works and how catastrophic the results can be. What made Shoemaker-Levy 9 extraordinary wasn't just Jupiter's role as a planetary shield. It was the timing. Modern astronomy had never recorded such an event, yet here was proof that giant impacts weren't just ancient history. The comet's breakup mirrored how asteroids fragment when approaching planets, giving clues about Earth's own bombardment history. Those dark Jupiter scars became a living classroom, teaching us how shockwaves propagate through atmospheres and how debris disperses after violent collisions, lessons that now inform asteroid defense strategies. Today, missions like NASA's DART probe, which intentionally crashed into an asteroid in 2022, owe part of their design to observations from 1994. Back then, we watched Jupiter take the hits. Now, we're learning how to deflect them. The Shoemaker-Levy 9 impacts didn't just change Jupiter's appearance for a few months. They changed how we see our place in a solar system where sometimes the sky really does fall. On June 8, 2004, astronomers around the world held their breath as a tiny, dark disk began its slow march across the face of the Sun, a sight unseen by human eyes since December 6, 1882. This was the transit of Venus, a cosmic alignment so precise it occurs in pairs separated by over a century, with each duo spaced exactly 8 years apart. The 2004 event wasn't just a celestial curiosity, it was the opening act of a scientific saga that would culminate in 2012, offering researchers a rare chance to refine techniques for measuring the universe itself. What made this transit historic wasn't just its rarity, it was the technological revolution it bridged. When Captain James Cook observed the 1769 transit from Tahiti, his team used pendulum clocks and handmade quadrants to time Venus's entry and exit. Their measurements, combined with data from other global expeditions, helped calculate Earth's distance from the Sun, the astronomical unit, with groundbreaking accuracy for the era. Fast forward to 2004, and space telescopes like Hubble had already pinned that distance down to the meter, yet Venus's transit still mattered. Modern scientists used it to test techniques for spotting exoplanets, alien worlds that crossed distant stars by studying how Venus's atmosphere bent sunlight, creating a telltale halo around its silhouette. The 2004 transit also delivered something Cook's team never saw: a global audience. Amateur astronomers in 70 countries documented the event, sharing images in real time across fledgling broadband networks. NASA's Trace satellite captured ultraviolet views of Venus's atmosphere glowing against the Sun's corona, while backyard observers used simple pinhole projectors to watch the planet's shadow crawl across paper screens. Unlike the dramatic black drop effect that plagued historical measurements where Venus's disk seemed to stretch like taffy as it crossed the Sun's edge, digital sensors and adaptive optics minimized distortion, yielding razor-sharp data. Perhaps most fascinating was how this transit revived old questions with new tools. Cook's voyage mapped the Pacific but also sparked colonial consequences. 2004's global collaboration with indigenous astronomers in Hawaii and Maori skywatchers in New Zealand contributing alongside NASA reflected a shifted perspective: the cosmos as shared heritage rather than imperial resource. When Venus finally exited the solar disk after 6 hours, it left more than data. It offered a mirror to humanity's journey, from wooden ships chasing shadows to satellites unlocking the secrets of alien suns. And it was just the first act. 8 years later, the curtain would rise again for a farewell performance no living person would witness again. On August 10, 1972, the American West woke up to a morning like any other, until the sky split open with a light brighter than the sun. A colossal fireball, estimated to weigh over 1,000 tons, screamed through Earth's atmosphere at 34,000 miles per hour, tracing a 200-mile path from Utah to Alberta. What made this meteor extraordinary wasn't just its size or speed. It was the fact that thousands witnessed it in broad daylight, a rarity for an event typically reserved for dark, moonless nights. Eyewitnesses described a spectacle ripped from science fiction, a searing white streak trailed by a twisting smoke plume, some reporting a thunderous sonic boom that rattled windows minutes later. Daytime fireballs like this defy expectations because most meteors burn up too high and too faintly to compete with sunlight. The 1972 event, later dubbed the Great Daylight Fireball, owed its visibility to sheer brute force. Plunging at a shallow 15-degree angle, the basketball-sized chunk of space rock skipped across the upper atmosphere like a stone on water, glowing white-hot as friction vaporized its surface. Unlike typical meteors that disintegrate in seconds, this one surfed the sky for nearly 2 minutes, an eternity in cosmic terms, allowing cameras across Montana and Wyoming to capture its descent. One famous photo snapped by a tourist at Grand Teton National Park shows the fireball blazing past the mountain range, its tail fanning out like a celestial paint stroke against the blue. Scientists later determined the meteor was a rare Earth grazer, a category of space rock that ricochets off our atmosphere rather than burning up or impacting. Most meteors hit the atmosphere like a dart hitting a board, plunging steeply and quickly. Earth grazers, by contrast, arrive at oblique angles, allowing them to streak horizontally for hundreds of miles. The 1972 fireball came so close, skimming just 35 miles above Montana, that it briefly outshone Venus before soaring back into space, forever altered but intact. What makes these events so gripping isn't just their rarity, it's the raw unpredictability. Unlike eclipses or planetary alignments, fireballs give no warning. They turn ordinary moments into shared memories, like the thousands who stood slack-jawed on sidewalks that August morning. Some thought it was a missile, others swore they'd seen a UFO. For scientists, it was a golden opportunity. The fireball's prolonged visibility allowed precise trajectory calculations, suggesting it originated in the asteroid belt between Mars and Jupiter. Had its angle been steeper, it might have exploded like the Chelyabinsk meteor over Russia in 2013, releasing half a megaton of energy. Instead, it became a cosmic tourist visiting just long enough to leave us in awe before continuing its journey through the void. Today, fragments of the 1972 fireball likely still orbit the Sun, their path forever altered by Earth's gravity. For those who saw it, the memory lingers just as vividly, a reminder that sometimes the universe drops by unannounced, turning an average day into front-row seats for a once-in-a-lifetime show. And the next daylight fireball, it could happen tomorrow or not for centuries. That's the thrill of our cosmic neighborhood, always keeping us guessing. On the night of February 23, 1987, a star in our galactic backyard decided to go out with a bang, literally. In a distant corner of the Large Magellanic Cloud, a dwarf galaxy orbiting the Milky Way, a blue supergiant star collapsed under its own gravity, triggering a thermonuclear explosion so violent it briefly outshone its entire host galaxy. This was supernova 1987A, the closest stellar explosion witnessed in nearly 4 centuries, visible even to the naked eye despite being 168,000 light-years away. For astronomers, it was like winning the cosmic lottery, a front-row seat to a star's death throes, offering clues about how the universe seeds itself with the building blocks of life. What made SN 1987 extraordinary wasn't just its proximity. It shattered expectations from the start. Most supernovae come from red supergiants, but this one's progenitor star was hot, blue, and compact, a surprise that forced scientists to revise their models of stellar evolution. When its light finally reached Earth, neutrino detectors in Japan and the US picked up a ghostly pulse 2 hours before the visible explosion, proof that these elusive particles, produced in the star's collapsing core, outrace light when escaping a dying star. For the first time, humanity had multisensory evidence of a supernova, neutrinos signaling the collapse, followed by the visual fireworks. The aftermath played out like a cosmic detective story. As the explosion's shockwaves plowed through surrounding gas, they lit up pre-existing rings of material ejected by the star in its final millennia, creating a glowing hourglass visible only through telescopes. Heavy elements forged in the blast, like iron and gold, sprayed into space, destined to someday form new stars, planets, or even life. Meanwhile, astronomers tracked the expanding debris cloud, watching in real time as it grew from a point of light to a structured remnant over decades, a time lapse of stellar death unavailable for any previous supernova. But perhaps the most profound legacy of 1987 lies in its everyday impact. Every breath you take contains oxygen atoms forged in ancient supernova. The calcium in your bones, the iron in your blood, all were once hurled into space by explosions like this one. SN 1987 didn't just light up the southern sky, it illuminated our cosmic connection to the stars, proving we're quite literally made of stardust. And somewhere in the vastness of space, its light still travels outward, a beacon reminding the universe that even in death, stars give birth to new beginnings. Today, telescopes continue monitoring its expanding remnant, watching for the eventual formation of a neutron star or black hole at the crash site. But for those lucky enough to glimpse it in 1987, no instrument was needed. All they had to do was look up and witness a star's final, brilliant farewell, a message from the distant past, written in light and delivered across millennia. In the midst of a global pandemic, when the world felt isolated under lockdowns and uncertainty, the cosmos sent a dazzling reminder that beauty persists. Comet NEOWISE. Discovered in March 2020 by NASA, a near-Earth object wide-field infrared survey explorer mission, this icy visitor became the brightest comet visible from the northern hemisphere in over 20 years. By July, it had transformed into a celestial spectacle, glowing with a nucleus so luminous it could be seen without telescopes or even binoculars. But what made NEOWISE truly unforgettable wasn't just its brightness, it was its dramatic twin-tailed structure, a rare visual feast that turned casual skywatchers into avid comet chasers overnight. The comet's two distinct tails told parallel stories. The first, a glowing white dust tail, curved gently behind it like a painter's brushstroke, sunlight reflecting off tiny particles shed by the comet's nucleus as solar heat vaporized its icy surface. The second, a faint blue ion tail, shot straight out like a laser beam, made of charged gas molecules pushed away from the sun by solar wind. This duality revealed the comet's hidden dynamics. Dust responding to gravity, ions dancing to the sun's magnetic tune. Under dark skies, both tails stretched across 15 degrees of sky, roughly the length of an outstretched hand, creating an ethereal crosshatch pattern that astrophotographers raced to capture. Timing was everything for observers. In early July, the comet became visible just before dawn, hovering near the northeastern horizon like a cosmic exclamation point. By mid-month, it had transitioned to evening skies, climbing higher each night near the Big Dipper. Its peak brightness coincided with warm summer nights, inviting families to backyard stargazing sessions that doubled as pandemic escapes. Urban viewers faced challenges. Light pollution washed out the fainter ion tail, but those who ventured to darker locales witnessed a scene straight from medieval tapestries where comets were once considered omens. Instead of doom, NEOWISE delivered something far rarer, wonder. Photographers faced a golden opportunity. The comet's slow movement allowed for long exposures without star trails, while its position near familiar constellations provided perfect framing. Experts recommended DSLR cameras with wide-angle lenses, ISO settings around 800 to 1600, and exposures between 5 and 15 seconds to capture both tails' delicate structures. Some composite images blended short exposures of the bright nucleus with longer ones to reveal the wispy ion tail, techniques usually reserved for deep sky objects. Social media erupted with time lapses showing the comet's nightly progression. its tails shifting slightly as solar winds sculpted them in real time. Beyond its visual splendor, NEOWISE carried scientific intrigue. Spectral analysis revealed it was rich in cyanogen and diatomic carbon compounds common in primordial solar system material. Its 6,000-year orbit meant the last time it approached Earth, human civilization was in its infancy, the next visit likely not for millennia. For astronomers, it was a chance to study a pristine relic. For the rest of us, it was a shared moment of cosmic connection during a fractured time. People who'd never glanced at the night sky found themselves setting alarms for 3 a.m. viewings, trading tips on Reddit threads, or simply lying on rooftops, letting the comet's glow remind them that the universe carries on, indifferent to earthly troubles. As July waned, so did the comet's brilliance, fading into telescopic obscurity by August. But for those who witnessed it, NEOWISE left more than pretty photos. It offered proof that even in darkness, light finds a way, whether from a distant ball of ice or the collective awe of strangers looking up, together yet apart under the same ancient sky. On the morning of February 15, 2013, the people of Chelyabinsk, Russia, were starting an ordinary winter day until a fireball 30 times brighter than the sun tore across the sky at 42,000 miles per hour. The Chelyabinsk meteor wasn't just another space rock burning up harmlessly in the atmosphere. It was a 6,500-ton reminder of how vulnerable Earth is to cosmic surprises, detonating 14 miles above the city with the force of 450 kilotons of TNT, 26 times more powerful than the atomic bomb dropped on Hiroshima. What made this event unprecedented wasn't just its explosive power. It was the sheer volume of eyewitness footage capturing every jaw-dropping moment. Dashboard cameras, ubiquitous in Russia due to insurance requirements, recorded the fireball's spectacular descent from multiple angles. Videos showed the meteor's initial streak, a searing white line splitting the dawn sky, followed seconds later by a blinding flash as the shockwave shattered windows across 6 cities, injuring over 1,600 people. The explosion's thunderous boom rolled in minutes later, rattling buildings hundreds of miles away and triggering car alarms as far as Kazakhstan. Scientists later determined the shockwave circled the globe twice, detected by infrasound stations designed to monitor nuclear tests. The Chelyabinsk meteor's legacy extends far beyond broken glass. Its shallow 12-degree entry angle allowed it to penetrate deeper into the atmosphere than most meteors, resisting disintegration until extreme pressure and heat finally vaporized it. Fragments recovered from nearby Lake Chebokul revealed it was a stony chondrite, a common but fragile asteroid type that rarely survives atmospheric entry intact. Most sobering, the rock approached from the sun's direction, completely invisible to telescopes until it was already burning through the sky. This blind spot forced a reckoning in planetary defense. Unlike the fictional asteroid strikes of Hollywood, Chelyabinsk demonstrated how even relatively small objects just 65 feet wide could wreak havoc without warning. In its aftermath, NASA expanded its near-Earth object monitoring programs, funding new telescopes like Atlas in Hawaii designed to spot incoming threats weeks rather than hours in advance. The event also spurred international cooperation, with the United Nations establishing the International Asteroid Warning Network to coordinate global response strategies. Yet amid the chaos, Chelyabinsk also gifted science with an unexpected trove of data. Seismic stations recorded the airburst's energy release in real time, helping calibrate models for future impact assessments. Satellite observations tracked the dust plumes spread across the stratosphere, where it lingered for months, briefly cooling the planet. Even the injuries, mostly cuts from flying glass, provided lessons in disaster preparedness, revealing how standard window treatments could mitigate future meteor-related casualties. Perhaps the most haunting detail, the Chelyabinsk meteor wasn't alone. Just 16 hours later, the much larger asteroid 2012 D14 skimmed past Earth at a distance closer than some satellites, a cosmic coincidence underscoring how much still slips through our detection nets. Today, fragments of the meteor are displayed in museums worldwide, not as curiosities but as warnings carved in stone from space. Next time we might not get lucky. The next time the rock could be bigger, and the next time it might not break apart in the sky. In late August 2003, the red planet decided to put on its grandest show in 60,000 years, a close encounter that turned Mars from a distant speck into a glowing orange disk visible to the naked eye. On the 27th, Earth and Mars came within 34.6 million miles of each other, the tightest squeeze since the time when Neanderthals still walked the plains of Europe. To the unaided eye, Mars blazed at magnitude -2.9, outshining every star in the night sky except Sirius, while telescopes revealed details usually reserved for spacecraft cameras. What made this opposition historic wasn't just the raw proximity. It was the celestial geometry. Mars' orbit is an eccentric ellipse, meaning some close passes bring it nearer than others. The 2003 approach coincided with perihelion, Mars' closest point to the Sun, amplifying the effect. Through even modest backyard telescopes, the planet swelled to an unprecedented 25 arcseconds across, 6 times larger than during its faintest appearances. Suddenly, features like the icy polar caps, dark volcanic plains of Syrtis Major, and the sprawling rust-colored deserts of Arabia Terra snapped into crisp focus. Amateur astronomers reported seeing surface markings typically requiring professional-grade optics, while Hubble captured razor-sharp images of a dust storm churning near the Hellas Basin. The event turned into a global star party. From Tokyo to Tucson, people gathered on rooftops and in parks, sharing telescopes to glimpse Martian grandeur. Some observers used simple smartphone adapters to photograph the planet's gibbous phase, a sight impossible to see with the naked eye due to Mars' small apparent size most years. Seasoned astrophotographers exploited the rare clarity to image intricate cloud formations over Olympus Mons, the solar system's tallest volcano, while science classrooms projected Mars' disk onto whiteboards using basic refractors. But the real magic lay in the timing. Just weeks earlier, NASA had launched the Spirit and Opportunity rovers, capitalizing on the orbital alignment to shorten their journey to Mars. Those missions would later rewrite our understanding of the planet's watery past, but in August 2003, all eyes were on the sky. As urban light pollution faded the Milky Way from view for many, Mars burned defiantly bright, a reminder that cosmic wonders still exist even in our modern, screen-dominated lives. The 2003 record won't be broken until August 28, 2827, when Mars edges slightly closer, but few alive today will witness that encounter. For those who stood beneath that August sky 2 decades ago, the memory remains etched like a planetary Polaroid, a night when the red planet stopped feeling distant and became, just for a moment, a world you could almost reach out and touch. The night of March 19, 2011, felt different from the moment the moon rose, a golden orb swelling on the horizon, its glow so intense it cast sharp shadows across parking lots and backyards. This was no ordinary full moon. It was a supermoon, a term coined not by scientists but pop culture, describing the moon's closest approach to Earth in nearly 2 decades. At 221,565 miles away, it appeared 14% larger and 30% brighter than a typical full moon, a difference subtle to casual observers but striking when photographed side by side with its farthest counterpart. What made this lunar event fascinating wasn't just its size, it was the tidal tug of war it triggered. As the moon's orbit brought it nearest to Earth, a point called perigee, its gravitational pull amplified ocean tides, creating what's known as perigean spring tides. Coastal towns from Maine to Florida braced for higher than usual surges, though the actual impact varied. In some places, tides rose just inches above normal. Others, like Fundy Bay in Canada, saw dramatic tidal bores. But contrary to wild internet claims, the supermoon didn't cause earthquakes or volcanic eruptions. The myth stems from a misunderstanding of gravity's scale. While the moon's pull moves oceans, Earth's crust remains largely unaffected by these orbital nuances. To appreciate why this supermoon stood out, picture the moon's orbit as an oval, not a perfect circle. Each month, it swings between perigee closest and apogee farthest, varying its distance by about 30,000 miles. But even perigees aren't created equal. In 2011, the moon's closest pass aligned almost perfectly with the full phase, a rare synchronicity that hadn't happened since 1993 and wouldn't recur with such intensity until 2034. Astrophotographers seized the moment, capturing composite images comparing the supermoon to a micromoon, full moon at apogee, revealing a stunning size contrast. The moon's apparent diameter, usually around half a degree in the sky, swelled noticeably, making craters like Tycho and rays from Copernicus appear crisper through telescopes. The event also highlighted a quirk of human perception. When the moon hangs low near the horizon, it often looks enormous due to the moon illusion, a trick of the brain that compares it to distant trees or buildings. During the supermoon, this effect combined with its actual proximity, creating a spectacle that felt almost cinematic. Social media buzzed with photos of the moon looming behind landmarks, from the Eiffel Tower to Sydney's Opera House, though many of these images relied on clever zoom lenses rather than raw celestial mechanics. For scientists, the 2011 supermoon offered more than pretty pictures. Precise laser measurements from reflectors left by Apollo missions confirmed subtle fluctuations in Earth-Moon distance, refining models of orbital decay. Meanwhile, tidal gauges recorded how coastal ecosystems responded to the extra gravitational squeeze, with some marshes experiencing unusual nutrient mixing that benefited shellfish beds. The supermoon's legacy endures as a lesson in celestial intimacy, a reminder that even familiar objects like the moon still harbor surprises. It wasn't a world-ending omen or a seismic trigger as some feared. Just a quiet cosmic dance, timed perfectly to remind us that beauty often lies in the details, especially when those details loom larger than usual in the night sky. The spring of 2014 marked the beginning of an eerie celestial sequence, 4 blood-red total lunar eclipses unfolding like clockwork over the next 2 years, each separated by precisely 6 lunar cycles. This was no random alignment. Known as a lunar tetrad, this phenomenon packs all 4 eclipses into consecutive full moons without partial eclipses in between, a pattern so rare it's occurred only 8 times since the year 1000. But what turned heads wasn't just the astronomy. These blood moons coincided with Jewish holidays both years, sparking ancient prophecy debates and viral doomsday predictions that eclipsed the science itself, pun intended. To understand why tetrads feel so supernatural, we need to peel back the orbital mechanics. Lunar eclipses happen when Earth slides directly between the Sun and Moon, casting our planet's shadow across the lunar surface. But for a tetrad to occur, the geometry has to be flawless. The Moon's orbit tilts 5 degrees relative to Earth's, meaning most full moons pass just above or below our shadow. Only when alignment intersects perfectly, typically during periods when the Moon's orbit is at its closest to Earth, do we get this 4 eclipse winning streak. The 2014 tetrad was special because it happened during a cycle of exceptionally close full moons, making each blood moon appear slightly larger and darker than usual. Now let's separate cosmic fact from folklore. The term blood moon itself isn't scientific, it's a colloquial name for the coppery glow caused by sunlight refracting through Earth's atmosphere during totality, much like how sunsets paint the sky red. But when pastors and conspiracy theorists noticed all 4 eclipses landed on Passover and Sukkot in both 2014 and 2015, ancient texts suddenly got fresh attention. Some pointed to the Book of Joel's line about the moon turning to blood, while others cited historical tetrads coinciding with events like Israel's founding in 1948. The truth, while the Jewish calendar is lunar-based, making eclipse alignments more likely, NASA records show tetrads have matched these holidays at least 7 other times in the past 2 millennia with no corresponding historical upheaval. For astronomers, the real spectacle was the eclipses themselves. Unlike the quick drama of a solar eclipse, each blood moon offered a leisurely show, with totality lasting over an hour. The April 15, 2014 event set the tone, visible across North and South America with a deep crimson hue due to high-altitude volcanic ash from earlier eruptions. The October 8 eclipse treated Asia and Australia to a similar display, while the April 4, 2015 event turned the moon a striking orange over Western North America. Photographers reveled in the challenge of capturing the moon's changing colors, stacking exposures to show its transition from silver to rust. Time lapses revealed something naked eyes couldn't see: stars winking into view around the eclipsed moon as daylight faded in the lunar sky. The tetrad's scientific legacy went beyond pretty pictures. Researchers used these events to study Earth's atmospheric chemistry by analyzing how different wavelengths of sunlight filtered through our ozone layer reached the moon. Meanwhile, historians dug into how past cultures interpreted tetrads, from Shakespeare's ominous references in King Lear to Native American tribes viewing them as celestial cleansings. The final eclipse on September 28, 2015 offered a fitting finale, a supermoon eclipse where the moon appeared both larger and redder simultaneously, a combo not seen since 1982. By the time the tetrad concluded, one thing was clear. Whether you saw it as divine signaling or orbital poetry, this sequence reminded us that the sky doesn't need superstition to inspire awe. The precision required for 4 blood moons to march across 2 years, each time to ancient holidays, was wonder enough. And for those who missed it, mark your calendars for 2032 when the next tetrad begins. Just don't expect the world to end. The universe has always been dramatic. It's our interpretations that keep changing. The night of November 18, 2001, transformed the sky into a celestial fireworks display unlike anything seen in decades, the legendary Leonid meteor storm. For those lucky enough to witness it under dark skies, the heavens seemed to crack open, raining down streaks of light at rates exceeding 2,000 meteors per hour at its peak. Unlike typical meteor showers offering a handful of shooting stars per minute, this was a full-blown cosmic avalanche, with fireballs so bright they cast fleeting shadows on the ground and left glowing trails that lingered for seconds. The cause: Earth plowing through an exceptionally dense debris trail left by a temperamental cosmic traveler, comet Tempel-Tuttle. This icy visitor, which swings by the sun every 33 years, acts like a messy gardener scattering gravel across its orbital path. Normally, Earth's annual pass through the Leonid stream delivers modest shows of about 15 meteors per hour. But when our planet intersects with a fresh, tightly packed cluster of comet debris, like those ejected during Tempel-Tuttle's close passes in 1866 and 1966, the result is a meteor storm. The 2001 event benefited from a perfect trifecta. Recent comet activity in 1998 had deposited new material. Jupiter's gravity had herded those particles into Earth's path, and timing placed the storm's peak over Asia and North America during pre-dawn hours, when the constellation Leo, the meteor's apparent radiant point, rode high in the sky. What made the Leonids so electrifying was their unpredictability. Meteor showers are usually reliable clockwork, but storms like this defy precise forecasting. Tiny gravitational nudges from planets or outgassing from the comet itself can shift debris trails by thousands of miles, enough to make the difference between a dud and a deluge. Just hours before the 2001 storm, models disagreed on whether rates would hit 300 or 3,000 per hour. The uncertainty added to the thrill. Observers from the Mojave Desert to Mongolia watched the sky with a gambler's anticipation, knowing they might see history or just a typical shower. When the storm finally erupted, it delivered fireworks in waves, with brief but jaw-dropping outbursts where 6 or more meteors streaked across the sky simultaneously. The storm's legacy lives on in more than memories. Satellite operators used it to test shielding against potential impacts, since even millimeter-sized particles traveling at 150,000 miles per hour can damage spacecraft. Astronomers, meanwhile, refined debris trail prediction models lessons now applied to newer showers like the December Geminids. For those who stood beneath that November sky, though, the takeaway was simpler, a visceral reminder that the universe is anything but static. Comets shed, planets pivot, and sometimes, if the cosmic dice roll just right, the sky remembers to show off. On October 19, 2017, astronomers in Hawaii spotted something extraordinary, a faint dot racing across the sky that didn't belong to our solar system. This wasn't your average asteroid or comet. It was the first confirmed interstellar visitor ever detected, a cosmic drifter from another star. Named Oumuamua Hawaiian for Scout, this mysterious object defied every expectation, leaving scientists scrambling to explain its bizarre features before it vanished into the depths of space. The first shock came with Oumuamua's shape. Most asteroids and comets are vaguely round or lumpy. This thing was different, a tumbling, cigar-shaped rock at least 6 times longer than it was wide, stretching an estimated 600 feet from end to end. Telescopes couldn't resolve its surface, but light curve analysis revealed it spinning chaotically every 7 to 8 hours like a poorly thrown football. Even stranger was how it moved. As it slingshotted past the sun, it accelerated in ways gravity alone couldn't explain, as if pushed by some unseen force. That's when speculation exploded. Comets typically speed up due to outgassing sunlight vaporizing their ice, creating a natural rocket effect, but Oumuamua showed no visible coma or tail. Some scientists proposed it might be a hydrogen iceberg sublimating invisibly, or an exotic dust bunny made of ultra-porous material. Others dared to voice the unthinkable. Could this be alien technology, a derelict light sail or spacecraft? The theory, led by Harvard astronomer Avi Loeb, pointed to Oumuamua's unusual reflectivity and acceleration pattern, eerily similar to how a thin solar sail would behave. The truth remains elusive. By the time astronomers realized what they were seeing, Oumuamua was already racing away at nearly 200,000 miles per hour, too distant for follow-up observations. What data we have suggests a natural origin, possibly a fragment from a Pluto-like exoplanet, shredded by tidal forces and flung into interstellar space. Its reddish hue hints at organic rich ices baked by cosmic rays over millions of years, but that doesn't fully explain the acceleration mystery, leaving room for debate. Beyond the sci-fi allure, Oumuamua's real legacy is how it changed astronomy. Before 2017, no one knew interstellar visitors could be detected. Now, thanks to improved sky surveys like Pan-STARRS, we've spotted a second, the comet Borisov in 2019, proving Oumuamua wasn't a fluke. These drifters are cosmic postcards, carrying secrets about how planets form around other stars. Future telescopes like the Vera Rubin Observatory will likely find dozens more, maybe even one slow enough to chase with a probe. So was Oumuamua alien tech? Probably not, but that's almost beside the point. Its greatest gift was the reminder that the universe is far stranger and more generous with its mysteries than we ever imagined. Every now and then, it sends a scout to rattle our assumptions, proving there's always more to discover. On April 13, 2029, an asteroid the size of 3 football fields will streak across our skies closer than some weather satellites, and you won't need a telescope to watch it happen. Asteroid Apophis, named after the Egyptian god of chaos, will skim just 19,000 miles above Earth's surface. so near it'll cross an imaginary line where our planet's gravity starts overpowering the Moon. At that range, observers in parts of Europe, Africa, and Asia may see it as a fast-moving star, gliding across the sky faster than a jetliner over the course of about 2 hours. What makes this encounter extraordinary isn't just the proximity, it's the precision of our predictions. When Apophis was first discovered in 2004, astronomers calculated a terrifying 1 in 37 chance it could strike Earth in 2029. Further observations quickly ruled out collision, but the asteroid's sheer size, 1,100 feet wide, and speed 25,000 miles per hour, kept it high on NASA's threat list. Today, thanks to radar studies during its 2021 flyby, we know its path with pinpoint accuracy. The 2029 approach will actually tweak Apophis' orbit through gravitational interactions, ensuring it won't threaten Earth for at least another century. Dispelling doomsday myths is half the battle. Unlike Hollywood's sudden, city-smashing space rocks, real planetary defense operates in slow motion. NASA's Center for Near-Earth Object Studies has tracked Apophis for decades, refining its trajectory down to a few hundred meters. The 2029 pass will be so close that Earth's gravity will stretch the asteroid's shape slightly, possibly triggering minor quakes on its surface, a phenomenon scientists call tidal disruption. 4 hours after closest approach, Apophis will enter a zone where satellites like NOAA weather monitors orbit, though the chance of collision remains effectively zero. For skywatchers, the real thrill lies in accessibility. At peak brightness, Apophis could reach magnitude 3, as visible as the stars in Orion's belt, though its speed will make it stand out. Unlike slow-moving planets or steady stars, the asteroid will traverse the width of the full Moon every few minutes. Observers in dark sky locations might even glimpse its movement in real time, an effect usually reserved for close-passing airplanes. Smartphone astrophotography could capture its motion with simple tripod-mounted exposures, while backyard telescopes will reveal its changing position against background stars from minute to minute. This event isn't just a celestial close call, it's a golden scientific opportunity. Radar telescopes at Goldstone and Arecibo, weather permitting, will map Apophis' surface in unprecedented detail, potentially spotting boulders or craters as small as a few meters across. The flyby's gravitational nudge will also let researchers calculate the asteroid's mass and density, clues to whether it's a solid rock or a loosely bound rubble pile. Future missions like ESA's Ramses might even rendezvous with Apophis post-flyby to study how Earth's gravity altered its structure. What about the lingering what-ifs? Even if Apophis' orbit hadn't been deflected, its impact would have released energy equivalent to 60,000 Hiroshima bombs, devastating on a regional scale but far from civilization ending. NASA's ongoing DART mission and planetary defense programs aim to spot and deflect such objects decades in advance, so when 2029 arrives, don't brace for disaster, look up. That speeding dot isn't doom. It's proof we've learned to read the cosmos well enough to watch danger pass us by. In July 1961, American satellites designed to monitor nuclear tests picked up a signal that defied explanation, a brief, intense burst of gamma rays coming not from Earth but from deep space. At first, scientists suspected a malfunction or Soviet space weapon, but as more of these flashes appeared in the data, they realized they'd stumbled onto something far more extraordinary. The universe's most violent explosions, capable of unleashing more energy in seconds than our Sun will emit in its entire 10 billion-year lifespan. These were gamma-ray bursts, cosmic detonations so powerful they can briefly outshine every star in their host galaxy combined. The mystery deepened when astronomers couldn't pinpoint their origins. Unlike supernova or pulsars, GRBs left no visible afterglow with 1960s technology. For decades, they remained celestial ghosts until 1997, when the Beppo-SAX satellite finally linked a GRB to a distant galaxy. The revelation was staggering. These bursts weren't local oddities but events occurring billions of light years away, meaning their true energy output was almost unimaginable. We now know they come in two flavors. Short bursts lasting under 2 seconds arise when neutron stars collide in a kilonova explosion, spraying heavy elements like gold across space. Long bursts lasting minutes signal the death throes of massive stars collapsing into black holes, their cores launching jets of plasma at nearly light speed. Imagine a star 30 times heavier than our Sun running out of fuel. Its core implodes instantly, forming a black hole while the outer layers collapse inward like a skyscraper in freefall. This triggers a hypernova, a supernova on steroids where twin particle jets drill through the dying star like cosmic blowtorches. These jets, channeled by magnetic fields trillions of times stronger than Earth's, punch into interstellar space, accelerating particles to near light speed. The result, a gamma-ray beam tighter than a laser pointer, visible across the universe if aimed our way. What makes GRBs terrifyingly fascinating is their potential for destruction. A nearby burst within 6,000 light-years could strip Earth's ozone layer, triggering mass extinctions. Some scientists suspect a GRB contributed to the Ordovician extinction 450 million years ago. Yet these same cataclysms may have seeded the cosmos with elements necessary for life. Their jets forge rare heavy metals, while the radiation could spark probiotic chemistry on distant worlds. Today, satellites like Swift and Fermi catch hundreds of GRBs annually, each a fleeting glimpse into the universe's most extreme physics. The 1961 detection wasn't just a scientific accident, it was a wake-up call. Hidden in the cosmos are forces that make hydrogen bombs look like firecrackers, reminders that the universe operates on a scale we're only beginning to comprehend. And every burst we detect carries a message. Out there, stars are dying in ways that redefine the word explosion. In December 1995, astronomers pointed the Hubble Space Telescope at what seemed like the most mundane patch of sky imaginable, a dark, nearly empty spot in Ursa Major, no larger than a grain of sand held at arm's length. For 10 consecutive days, Hubble's camera gathered light from this seemingly insignificant void, capturing photons that had traveled for billions of years. The result wasn't just another pretty space picture. It was a cosmic census, an image that rewrote our understanding of the universe's grandeur. The Hubble Deep Field revealed over 3,000 galaxies crammed into that tiny sliver of darkness, each a sprawling island of stars, some so ancient they existed when the universe was barely 5% of its current age. What made this image revolutionary was its depth of vision. Before Hubble, even our most powerful telescopes could only peer so far into the cosmos. But by staring at one spot for days collecting light like a slow exposure photograph, Hubble acted as a time machine, capturing galaxies so faint they'd never been seen before. Some appeared as shapeless red smudges, primordial galaxies still in their infancy, their light dating back over 12 billion years. Others showed bizarre morphologies, cosmic train wrecks of colliding spirals, ghostly rings, and clusters so distant their combined glow had been stretched into infrared by the expansion of the universe itself. The sheer diversity hinted at a cosmos far more crowded and dynamic than anyone had imagined. The real magic lay in the perspective shift. That grain of sand-sized patch represented roughly 1/24 millionth of the entire sky. Extrapolated across the heavens, it suggested the observable universe contained at least 100 billion galaxies, a number so vast it redefined empty space. Suddenly, every sci-fi trope about endless frontier felt quaint. Here was proof that even the darkest voids teemed with starlight, most of it too faint for human eyes to ever see unaided. The deep field became a mirror held up to our own insignificance, and yet, paradoxically, a testament to human curiosity. We'd built a machine that could see farther than evolution ever intended. Scientific insights poured in from this single image. The abundance of young, irregular galaxies supported theories that cosmic structures grew hierarchically, small clumps merging over time to form giants like our Milky Way. The redshift distribution of galaxies provided a snapshot of the universe's expansion rate at different epochs, refining estimates for its age and composition. Perhaps most hauntingly, some of those ancient galaxies no longer exist as we saw them. Their light took so long to reach us that by now they've likely collided, faded, or been consumed by supermassive black holes, their stories ending billions of years before Earth even formed. For astronomers, the deep field was more than data. It was a philosophical pivot point. Suddenly, every blank sky patch became a potential treasure chest of cosmic history. Later deep fields, like the ultra-deep field in 2004 and the E-extreme deep field in 2012, pushed even further, revealing galaxies from just 450 million years after the Big Bang. But none carried the shock of that first revelation, when humanity pulled back the curtain and realized the universe wasn't just vast, it was crowded with ghosts, each whispering secrets across the dark. Today, the original Hubble Deep Field hangs in museums and textbooks, not as an endpoint but as an invitation. Its galaxies remind us that every time we look deeper, the universe gets stranger. And when the James Webb Space Telescope turned its infrared eyes to the same patch of sky in 2022, it uncovered hundreds more galaxies hidden even from Hubble, proof that the cosmos always keeps one more card up its sleeve. The true legacy of the deep field isn't the galaxies it revealed, but the question it etched into our collective imagination. If so much hides in darkness, what else might be out there waiting for the right tools and the right moment to be seen? On April 10, 2019, humanity peeled back the curtain on one of space's most elusive enigmas, a supermassive black hole lurking 55 million light-years away in galaxy M87. The image, resembling a fiery ring with a dark abyss at its center, wasn't just a scientific milestone. It was a triumph of global cooperation, a validation of century-old physics, and a visual manifesto proving these cosmic monsters weren't just theoretical ghosts. They were real, they were messy, and they bent the very fabric of reality. The Event Horizon Telescope didn't operate like a traditional observatory. Instead, it transformed our planet into a giant radio receiver by linking 8 telescopes across 4 continents, from the alpine heights of the South Pole to the volcanic peaks of Hawaii. Synchronized by atomic clocks accurate to within 1 second every 100 million years, this network achieved resolution sharp enough to spot a donut on the moon. For 10 days in April 2017, these dishes collectively stared at M87's core, gathering petabytes of data so massive it had to be shipped on hard drives for processing. 2 years of supercomputer crunching later, the now iconic orange donut of doom emerged, a glowing ring of billion-degree plasma swirling at near light speed, framing the black hole's event horizon like a cosmic bullseye. That shadowy center, that's where physics gets weird. The dark patch isn't the black hole itself. It's the point where gravity grows so strong that even light can't escape, creating a silhouette against the hot gas behind it. The lopsided glow comes from relativistic beaming, a phenomenon predicted by Einstein where material orbiting toward us appears brighter due to mind-bending spacetime distortions. The shape and size matched Einstein's equations with uncanny precision, proving general relativity holds true even in gravity's most extreme arena. Beyond confirming textbook physics, the image revealed surprises. The black hole's spin axis tilted oddly relative to its jet, a colossal particle beam shooting thousands of light-years into space. This misalignment hinted at chaotic growth, possibly from multiple black holes merging over eons. The ring's brightness also flickered over observations, offering real-time glimpses of a feeding black hole's turbulent table manners. For scientists, the photo capped decades of indirect evidence, from star orbits to gravitational waves, finally giving these invisible giants a face. For the public, it rendered the abstract tangible, a celestial vortex massive enough to swallow solar systems, yet governed by rules scribbled on paper a century prior. And the best part, this was just the opening act. With more telescopes joining the array, future images promise sharper views, perhaps even movies of black holes in motion, a front-row seat to spacetime's most violent dance. On September 26, 2022, a refrigerator-sized spacecraft named DART hurtled toward a tiny asteroid at 14,000 miles per hour, and humanity scored its first cosmic hole-in-one. The target was Dimorphos, a moonlet barely 530 feet wide orbiting the larger asteroid Didymos, chosen because its binary system posed no threat to Earth while offering perfect conditions for a real-world deflection test. As DART camera streamed the final heart-pounding moments before impact, scientists at Johns Hopkins Applied Physics Laboratory erupted in cheers. This wasn't just another space probe landing. It was our species' first intentional act of planetary defense, proving we could nudge a celestial object off course if one ever threatened our world. The mission's genius lay in its simplicity. Unlike Hollywood's nuclear solutions, DART, short for Double Asteroid Redirection Test, used pure kinetic energy as its weapon. Weighing just 1,200 pounds, the spacecraft functioned like a high-speed cosmic bullet, transferring its momentum to Dimorphos upon impact. The goal wasn't destruction, but deflection, altering the moonlet's orbit around Didymos by fractions of a percent. While that sounds modest in spaceflight terms, even a slight course change years in advance could make the difference between a near miss and a catastrophic impact. What happened next exceeded expectations. Precise measurements from Earth-based telescopes revealed Dimorphos' orbit had shortened by a staggering 32 minutes, far more than the minimum 10-minute change NASA hoped for. This unexpected success hinted the asteroid was likely a loose rubble pile rather than solid rock, with the impact ejecting thousands of tons of debris that acted like a natural rocket thruster, amplifying the push. Italian space agency's Liscia Cube, a shoebox-sized satellite released before impact, captured breathtaking images of the aftermath, a vast debris plume stretching thousands of miles, resembling a comet's tail forced into existence by human hands. Beyond the technical triumph, DART rewrote planetary defense strategy. Prior to this mission, asteroid deflection remained theoretical, with options ranging from gravity tractors using a spacecraft's gentle pull to ion beam shepherds. Now, kinetic impactors have vaulted to the front of the toolkit thanks to their proven effectiveness and relative simplicity. The mission also showcased the importance of early detection. NASA's ability to precisely track Didymos and Dimorphos for years beforehand proved critical for measuring DART's success. The implications ripple far beyond one small moonlet, with over 30,000 near-Earth asteroids currently catalogued, and an estimated 2/3 of potentially hazardous ones still undiscovered. DART offers more than peace of mind. It's a blueprint for survival, showing that when the next asteroid threat emerges, we won't be helpless bystanders. Upcoming missions like ESA's HERA will study Dimorphos crater in 2026, refining our understanding of impact physics. But for now, that grainy final image of DART camera going dark remains a landmark the moment humanity grew up enough to protect its cosmic backyard. Mark your calendars for April 8, 2024, because darkness is coming to North America in the middle of the day, and this time it's bringing friends. The upcoming Total Solar Eclipse won't just be a rerun of 2017's celestial spectacle. It's packing double the drama, with totality lasting up to 4.5 minutes in some locations, nearly twice as long as its predecessor, and carving a wider, more populous path from Mexico's Pacific coast up through Texas, the Midwest, and into eastern Canada. Nearly 32 million people already live inside this year's path of totality, with major cities like Dallas, Indianapolis, and Buffalo positioned for front-row seats. No cross-country road trips required this time. For millions, the show will unfold right overhead. scientists are gearing up for groundbreaking studies during those precious minutes when the sun vanishes. NASA plans to launch sounding rockets from Virginia to study how the sudden drop in sunlight affects Earth's ionosphere, a layer of the atmosphere critical for radio communications. Meanwhile, citizen scientists will document temperature drops and animal behavior, building on bizarre findings from 2017 where bees stopped buzzing and orb weaver spiders dismantled their webs mid-eclipse. But the real star might be the sun itself. With our home star nearing its 11-year activity peak, viewers could witness massive solar prominences, loops of plasma larger than Earth, arching from the eclipsed sun's edges like fiery cursive against the blackness. Choosing where to watch becomes part of the adventure. Mazatlan, Mexico offers beachside totality at 11 in the morning with palm-fringed views of the moon's shadow racing across the Pacific. In Texas, the hill country near Fredericksburg promises some of the clearest skies statistically, while Carbondale, Illinois, dubbed Eclipse Crossroads for lying in both 2017 and 2024 paths, throws a massive festival. Niagara Falls presents a surreal tableau. If skies are clear, visitors will see the mist-lit waterfall plunge into darkness at 3 in the afternoon. What makes this eclipse especially nerve-wracking? Weather. April's fickle skies mean cloud cover could turn totality into a dimming effect rather than a starry midday night. Veteran eclipse chasers often hedge their bets by plotting last-minute dashes along interstate highways toward clearer skies. Smart newcomers book flexible hotel cancellations and monitor forecasts obsessively in the final days. For those who missed 2017, this is a second chance served on a cosmic platter, and for veterans, it's an entirely different beast, longer, darker, and traversing landscapes where the last total eclipse occurred in 1869. Pack your eclipse glasses, but leave expectations at the door. Nature doesn't do encores, it reinvents the show every time. The year 2061 marks a cosmic homecoming that grandparents might remember from childhood. Halley's Comet, our solar system's most famous icy wanderer, swinging back into view after its 75-year journey to the outer darkness. For those who caught its underwhelming 1986 appearance, when light pollution and an awkward orbital position left casual observers squinting at a faint smudge, this return promises redemption. Early projections suggest the comet could shine up to 20 times brighter than last time, potentially rivaling Jupiter's brilliance as it streaks past Earth in late July. But what's truly extraordinary isn't just the comet itself, it's how much the world has changed since we last saw it. Back in 1986, comet chasers relied on film cameras, printed star charts, and word-of-mouth alerts to track Halley's progress. This time, a global network of smart telescopes like Unistellar's digital scopes synced to smartphone apps will automatically locate and track the comet for anyone with Wi-Fi. Imagine pointing your phone skyward and seeing augmented reality labels highlight the comet's nucleus and tails in real time, while I adjust your backyard telescope's focus to capture perfect shots. Astrophotography, once the domain of experts with $1,000 setups, will become as simple as framing a selfie. Expect social media feeds to flood with hyper-detailed images from amateurs using gear that didn't exist last visit, multispectral filters revealing the comet's chemical fingerprints, or hydrogen alpha lenses isolating the glow of ionized gas in its plasma tail. The scientific payoff could dwarf even the spectacle. During its 1986 flyby, humanity's best close-up data came from the European Space Agency's Giotto probe, which survived just minutes in the comet's debris-filled coma before its camera was sandblasted into oblivion. This time, an armada of modern tools stands ready. James Webb's infrared eyes will analyze the composition of Halley's dust and ices, while radio telescopes like ALMA map the subsurface heat of its nucleus. Citizen scientists might contribute to projects like Zooniverse could crowdsource analyses of tail structure changes, offering real-time insights into solar wind dynamics. And if private space ventures hit their stride, we might even see drones or cube tags deployed to study Halley from closer range than ever before. Yet the comet's greatest gift might be generational storytelling. Parents who glimpsed it as kids in '86 will point it out to grandchildren, passing down not just a celestial sight but a living thread of collective memory. Schools will live stream its approach, planetariums will host comet parties, and somewhere a future astronomer will peer through their first telescope at that fuzzy streak, just as Edmund Halley did in 1682, and feel the same electric jolt of discovery. Halley's comet has been Earth's faithful clockkeeper for millennia, appearing unchanged to Babylonian stargazers and Mark Twain alike, but this visit will be different. We'll see it through lenses that didn't exist, share it in ways once unimaginable, and understand it more deeply than any generation before. And when it fades back into the dark, we'll leave something new for its next return. A digital fossil record of our curiosity, waiting to be unearthed in 2136. From gamma-ray bursts that outshine galaxies to comets that visit once every 50 millennia, we've traveled through 25 of the universe's most breathtaking displays, events where chance, cosmic mechanics, and sheer spectacle collide. Each one offers more than just a light show. They're scientific gold mines, cosmic clocks, and humbling reminders of how small our calendars are compared to the universe's timeline. Some, like total solar eclipses or the Great Conjunction, gift us front-row seats to orbital ballets planned billions of years in advance. Others, like Oumuamua or gamma-ray bursts, arrive unannounced, rewriting textbooks in their wake. What ties them all together is impermanence. These aren't reruns. Miss them, and you might wait lifetimes or geological epochs for an encore. The 2024 total eclipse won't repeat its exact path for another 366 years. Venus won't silhouette the Sun again until 2117, and Halley's comet, circle 2061 on your calendar now, or your next chance slips to 2136. That's the magic of astronomy. It's the only science where being absent for class means waiting centuries to retake the test. Yet beyond dates and data, these events share something deeper, an invitation to look up and remember we're part of something vast. When you witness a meteor storm or stand in the moon's shadow, you're not just observing physics. You're joining a chain of wonder stretching back to Babylonians tracking Venus and indigenous cultures predicting eclipses millennia before computers. Every eclipse chaser, comet photographer, or kid pointing at Saturn through a telescope is adding to that story, so keep watching the skies literally. Set reminders for April's eclipse. Note when Mars dazzles in 2035 or when the next Leonid Storm might ignite. Subscribe to stay ahead of cosmic surprises because the universe never checks our schedules. And when you do witness one of these rarities, take a second to savor the quiet truth beneath the spectacle. In a cosmos where stars die and galaxies spin, we get to be the ones who notice. However briefly, however imperfectly, against astronomical odds, we're here alive and awestruck, just as the cosmos decides to put on a show.